Last time we saw lots of examples of greedy algorithms and some of the techniques that we use to develop, to analyze the performance of those greedy algorithms. So, focusing on relative approximations. We did greedy algorithms. And in most cases, we analyzed those greedy algorithms versus a lower bound or upper bound on the optimum, because obviously we can't know we can't look at the exact solution, so we can't really compare our solution to the exact solution. Instead, we compare our solution to some bound on the exact solution. And if we're close to that, then the exact solution is trapped in between, and so we're close to the exact solution as well. So today we're going to move on to non-greedy algorithms, things that try to be a little bit more sophisticated in the algorithms that they use. And we're going to be asking the following sort of interesting question. Last time, almost all of the algorithms that we looked at had constant factor approximation ratios. Right? So, I mean, we had the log n for set cover. But a lot of the other problems that we looked at, including max cut, vertex cover, and P Cmax, they all had constant factor approximations. In fact, they all achieved approximation ratios of 2. And so somebody asked the very reasonable question, can we do better? Is 2 the approximation ratio for all problems? Or might there possibly be some problems that have approximation ratios better than 2? Or even might these problems have some approximation ratios better than 2? Yes? And so we're going to start looking at that question today. We are going to actually look at the question of, what is the best possible relative approximation that we can hope to achieve? So let's get started. We're talking about relative factor approximations. There are lots of constants better than 2. I'm actually going to show you a class of algorithms which can have any constant that you want as their approximation ratio. So we're actually going to look at approximation schemes. Okay. An approximation scheme is a family of algorithms such that for every epsilon, there exists an algorithm A sub epsilon that is a 1 plus epsilon approximation algorithm. So we're going to see today a number of problems where we can get approximation algorithms that are as good as we would like them to be, all in polynomial time. Okay, and so there's the natural definition of a polynomial approximation scheme. Or a PAS, is one where each A sub epsilon is a polynomial time algorithm. Okay. So this is quite a lot better than 2, right? Yes?
Are we also, does the polytime include the epsilon?
A very fair question. So we can demand even more. A fully polynomial approximation scheme so I was going to save that for later, but a fully polynomial approximation scheme, or FPAS, has each A sub epsilon have a running time that is polynomial in n and epsilon. Okay. And we will see some examples of each to make those definitions clearer. Yes? Yeah, sorry, 1 over epsilon. I mean, being polynomial in 1 over epsilon is being polynomial in epsilon. It's just a negative exponent instead of a positive one. Okay. Good. So let's introduce the problem that we're going to be starting to look at, which is knapsack, which we've already seen. Right? We talked about this last time. You've got your item sizes, Sj, and profits, Pj, for your n items. And you've got a knapsack size B. And you want to fit as much stuff, as much profit as possible into your knapsack. Okay. So we saw last time that this problem does not have an additive approximation at all because you can scale it and turn any additive approximation into an exact algorithm. But what I'm going to show you is that it has arbitrarily good approximation algorithms. However close you want to get to the optimum, you can. Okay. Now, we're going to start by looking at the special case of small integer profits. And I'm going to argue to you that when the profits are small integers, then in fact it's possible to solve this problem exactly. Okay, it's no longer NP hard. And then once we have figured out how to solve the problem when the profits are small integers, I will show you how to generalize that solution to a problem that has large integers or non-integer profits, and sacrifice only a little bit in the quality of the solution as you do that generalization. Okay? So for starters, how might we solve this problem with, when there are small integer profits? Well, this is a place where it's very natural to apply dynamic programming. Okay, so I am going to define B of JP to be equal to the smallest, and that's in sum of Sj terms, subset of items providing profit P. Yes?
What is J in the
Good. Sorry, thank you. It's the smallest subset of items providing profit P from among the set of items 1 through J. Okay. So if I hand you this definition, then sort of filling out what to do with it is sort of a standard application of dynamic programming. Yes, a question?
By subset, are you allowed to use the same items more than you're allowed to use the same items?
No, in the knapsack problem, I mean, you could do a variation of the knapsack problem where you're allowed to repeat use of items. But in the standard knapsack problem, each item is taken 0 or 1 times. Okay. So if I define this sort of magical, and so you can think of this as sort of a table, right? There are n possible values for J, and there are different possible values for P. Okay. Now, how can I use this, assuming that I fill out this table, and we'll figure out how to fill it out later. If I have this table all filled out, how can I use it to solve my knapsack problem? People seen dynamic programs before? Sorry, that was kind of a silly question. I guess you must have at some point. Right? Yes?
You look at when you include all the items and then just see when you can have a subset, like when the smallest subset is equal to the number of items.
Good.
Or
So,
the size.
right. So B of NP in particular, right, is equal to the smallest subset of everything. That has profit P, right? So for each value of P, I can tell you what's the smallest set of items that has profit P. So how do I use this in order to decide on the optimum solution to my knapsack problem? Yeah?
Look for the highest, look for the largest P such that the size of the small subset is smaller than B.
Good. So what I'm going to do is look for the maximum P such that this minimum size set can fit into the knapsack. Yeah? So this tells me that all I need to do in order to solve the knapsack problem is fill out this table of B of JP values, and then I can just read off my optimum, right? So how can I fill out this table of B of JP values? Yeah?
So B of J1P is the minimum of BJP and BJ minus 1, P minus S, J.
Good. So was that completely clear to everybody, or should we translate that into English?
So it's either the minimum including all items up to J, or it's the minimum subset if we get plus 1 of the value not summing up to the minus S.
Good. Good. So the key argument is that if we're trying to figure out what's the optimum structure, the optimum subset that uses the items from 1 through J plus 1, well, there's two choices. Either that optimum subset uses item J plus 1, or it does not, right? Now, if it does not use item J plus 1, then obviously we can just, it's going to be the same subset that achieves profit P using just the items from 1 through J, right? The other possibility is that it does use item J plus 1, right? And that means that right away, we're going to be using Sj plus 1 space for that J plus first item. But having done so, we don't need to achieve P profit anymore from the items 1 through J. It is sufficient to achieve profit P minus Pj. Okay? So we're just branching on these two possibilities of whether or not we use the J plus first item in the optimum subset. And in either case, we reduce to a problem sort of higher up in the table that we've already computed the value for. Yes? So this is, mathematically, this is just a recursive definition, but since we will have already computed these values and stored them, we don't have to actually do the recursive calculation. We just look in the table in two places. Yes?
Sorry, I'm a bit confused about the notation we're using. So Sj is a size, right?
Yes.
And Bj plus 1 is a subset.
So let me call this the size of the smallest subset. Yes? I mean, there's sort of this one-to-one association between the size of the subset and the subset itself. Yes?
That P minus Pj plus 1.
Oh, thank you. Yes. OK? Good. So how long does it take us to fill this table? Well, for each possible P, there are n values of J that have to be filled out. And of course, in order to fill out this value of P, you're only working with smaller values of P, right? So you can fill out one row of the table at a time, one for each value of P. And we can stop when we sort of know we've gotten far enough to have the optimum profit, right? So we can stop at P opt. Okay. And so that means that the runtime of this dynamic program is order n times P opt to fill out the table. Okay. Yes, sorry, this is definitely not profit exactly P. This is profit P or more. Okay. All right, so is this dynamic program clear, sort of how we solve it, why it gives us the optimum solution, and why it's polynomial time? But what is it polynomial in, right? Well, it's polynomial in n, but also in P sub opt, the optimum value of the solution. Notice, of course, that P sub opt is at most the sum of the pj's. Right? So we can also just say that this is polynomial in n and the sum of the pj's if we don't want to talk about the actual optimum value. So that's nice. We have an exact solution if the pj's are small integers. Right? If the pj's, for example, are polynomial in n, then our overall runtime is polynomial in n. Right? So we're all set as long as the p's are polynomial in n. But what if they're not? What if the p's are strange irrational numbers? Are we going to be, we're not going to be able to directly apply this dynamic program, right? Because we can't make a table entry for every possible irrational value of p. So what approach might we take if we have non-integers? Yeah?
Binning and logarithms?
Binning and logarithms.
Well, two separate things.
So tell me about logarithms. I'm curious about the logarithms.
Well, if you have really, really big numbers and you want to be able to say something that's polynomial in n instead of...
Oh, I see. So you're suggesting working with the logs of the numbers instead of the...
If they become enormously bigger or smaller.
Okay, so that's plausible except for the fact that our objective functions are kind of adding up the values of the numbers. And so we, if we've taken all the logs, we're going to have to multiply them back in order to do the additions, which is going to sort of kill our ability to keep the numbers small. Another way to look at it is that if you start with large integers and you take logarithms, you're not going to have integers anymore. And so again, it's going to be problematic to apply this kind of dynamic program approach. So is there something else that we can do? I mean, what's the easiest way to deal with non-integer numbers? Yeah? Round them. Right? Make them integers. If we make our numbers integers, then we don't have non-integer numbers anymore to worry about. Now, why is rounding often a good thing? Well, rounding is often a good thing because you're just taking off a little bit of the number and you're not changing anything by very much. Right? And if you're not changing anything by very much, well, that would seem to put us in good, situate us well to claim that we have a good approximation to the original problem. Okay? But we have to be a little careful. Why is it that we're not changing things very much? Well, because the rounded off part is small compared to the whole. So we have to make sure that the rounded part is small compared to the integer part. And if we start with, say, 1.9, we're not in that situation, right? The rounded part is quite large compared to the integer part. So how might we modify our problem in order to ensure that what we round is only a little bit of the integers that we have? Yeah?
Scale of the product?
Scale. So scaling and rounding go together very naturally, right? If we want to make sure that the fractional parts are small, let's start by multiplying everything by a large number to make everything big. And now any fractional parts that remain are certainly small and can be ignored. So we're going to apply scaling and rounding. Okay. And actually, this scaling approach is also going to solve the problem of when we have numbers that are really huge. Because if the numbers are really huge, then in a sense, the non-integer parts are too small. And we can make the numbers smaller without losing a lot. So let's assume that I know p. that I know the optimum. Okay. What I'm going to do is scale each price. So each pj is going to become, let me write pi because I'm getting really tired of my sloppy j's. I'm going to scale it by n over epsilon p times pi. And why do I pick this number? Well, this is going to be sort of my target approximation. I'm going to get within epsilon. And so my goal is going to be to make sure that any fractions that I get rid of are small compared to epsilon. So I'm going to scale it by this quantity, and then I don't actually need the parentheses, but I'm going to round it down. Okay. So this gives me a new set of prices, or profits rather. Okay. What do I do with this new set of profits? Well, find the optimum set given these new profits using the dynamic program. And I claim that without any changes, that it will be at least 1 minus epsilon times optimum of the original problem, i.e. 1 minus epsilon times p. Okay. The proof's not very hard. First thing to ask is, what does scaling do to the original optimum? So there is some subset that determines the original optimum, right? Its profits sum to p. Under scaling, what can I say about the profit of that subset? Well, I'm going to separate out the sort of the scaling and the rounding. Okay. So the scaling, what is the value of the profit after I scale? Yeah? Right. So scaling takes my profit p linearly to n over epsilon because I'm multiplying each piece of the profit by n over epsilon p. Now the interesting question, what happens when I round? What can happen to that profit of n over epsilon? Yeah? Well, I'm rounding down. So I'm going to do sloppy rounding. Since I'm a computer scientist, I don't care about details. What can decrease by 0.5? So it's a little worse than that, because remember that this profit comes from summing a bunch of individual profits. And what I'm scaling are the individual profits. So what can happen to each individual profit as a result of this rounding? Yeah?
Well, the individual profits can all be rounded down by 1, so you can have it like be n off the optimal profit.
Exactly. I lose about I lose at most 1 from each of the individual profits, right? Or 0.999 or whatever. That can happen to each profit. So I may end up with a profit of n over epsilon minus n. Okay. So this is the profit of the original optimum set. Now this set may no longer be optimum, right? The rounding may have punished it worse than some other set. But I can still achieve this profit using this set. Well, that tells me that when I run my dynamic program, it achieves profit at least n over epsilon minus n in the scaled and rounded version of the problem. Right? But that implies that the original profit of the set that I find is at least what? How do I figure out what, I find some set using this dynamic program, but this was with these scaled and rounded profits. So how do I find out what the original profit was for this set? Well, I need to unround, and I need to unscale. So what does that do to this n over epsilon profit, or n over epsilon minus n profit? Yeah?
Multiply by p epsilon over n gives you p minus p over epsilon.
Exactly. So I mean, I can't assume that I'll get anything at all from the unrounding, right? The particular profits that I work with may have been integers to start with after the scaling. But I certainly get to do the unscaling, which means that this becomes p epsilon over n times n over epsilon minus n, right? Which, wonder of wonders, just magically works out to be p times 1 minus epsilon. So I have found a subset that has value at least p times 1 minus epsilon. In other words, it is a 1 minus epsilon or 1 plus epsilon approximation, depending on whether you want to talk about numbers bigger than or less than 1. Okay. Now all we have to ask in order to finish this algorithm is about the runtime. Right? So what's the runtime of this algorithm? Everybody who kind of went to sleep when we were doing all that crazy math for linear programming has to now wake up and answer these easy questions, right? We're back to real algorithms now. All right, so what's the runtime here? Yeah?
It's like instead of n times p up, it's like n times p up times the scaling factor.
Exactly. It's n times the p opt in the scaled problem, right? And what we asserted right here is that p opt in the scaled problem is around n over epsilon, right? So it's n times the new p, or the scaled p opt, which is equal to n times n over epsilon or so, n squared over epsilon. Yes?
You assumed at the beginning we know the optimal p.
Ah, didn't I? I was hoping I would slip that by you. No, actually, I wasn't. I was hoping somebody would catch it so that I could explain what we do. OK? So it's good. So you caught me. So yes, I assumed at the beginning that we knew p. We don't know p. So we have to address that assumption, right? So if we don't know p, but we need to know p in order to run this algorithm, what should we do? Yeah?
Well, we can make a fairly good guess.
Guess p. That's exactly right, right? If you don't know, then you should guess. Okay. So let's imagine that we guess p. What's going to happen? If we guess p, we can run the algorithm, right? What's going to happen when we guess p and run the scaled algorithm? Well, there's kind of two interesting cases, right? So I could be optimistic or pessimistic, right? I might guess a p that's too large, or I might guess a p that's too small, right? What's going to happen if p is too large? So I'm guessing a profit that actually cannot be attained. Yeah?
You scale your PIs too much and you lose precision.
So I'll scale my PIs too much. I'll lose precision, right? What are the consequences going to be of scaling the PIs too small? Well, if I scale all the numbers to be too small, then my optimum is going to be too small. Right? So I won't find a value. I won't find a solution of value n over epsilon minus n because it won't exist. Right? So I'll find a solution that's too small. Right? I'll scale it up, and it won't work. Right? Actually, this is sort of overanalyzing the algorithm, right? In a sense, if I guess a p that's too large, I'm not going to find a solution to value 1 minus epsilon p. I can't, because there isn't one. So it doesn't actually matter what the algorithm does. I will fail if I guess p too large. Right? What if I guess p too small? Yeah?
The answer will be correct, but the running time will be correct. Answer will be better than what I answered.
Good. So one thing that I could do if I guess p too small is, you're right, I will sort of scale to numbers that are too big, right? And so I'll run the algorithm. And to find the optimum, I will end up running too long. I'll run much longer than n over epsilon time, or through more than n over epsilon layers. But actually, the way that I sort of define this algorithm, I'm just going to look for a solution of value n over epsilon. And I'll stop when I find one. So I'll still run for n over epsilon time. I will find a solution of value n over epsilon. And when I scale it up, I will find a solution of value 1 minus epsilon p. Right? So I will find a solution of value 1 minus epsilon p. So this is very nice, right? If I guess too big, one thing happens. If I guess too small, a different thing happens. In other words, I can know whether my guess is too big or too small. If I can tell whether my guess is too big or too small, how do I home in on the solution? Binary search. Okay? Okay. Yes?
Sorry, how can you check if it's too big or too small unless you know PR?
So by too small here, I mean compared to my target, right? So now that we've sort of worked through this, I'll run through it a different way. So if I guess this target p, right? So if I'm binary searching, I'm saying, let's try this p. So I'll try this p, and either I will succeed or fail in finding a solution of value 1 minus epsilon p. Right? If I fail to find a solution of value 1 minus epsilon p, it's because I guessed p too large. If I succeed in finding a solution of value 1 minus epsilon p, it's because I guessed p small enough, but maybe too small. So that tells me whether I need to divide my binary search upwards or downwards. Okay? So this almost finishes the story, but I do need starting points. Or sort of minimum and maximum p's. Right? Because the actual running time of the binary search is going to be based on how long it takes me to divide down between those two p-values. So what can I choose as lower and upper bounds on the possible values of p? Okay, so let's start for either one, but let's start with, yeah, go ahead.
I mean, for the lower bound, you can take 0, and for the upper bound, you can take the sum of the products.
Okay, so I could take 0 as a lower bound. A small problem with 0 is that it's infinitely smaller than any upper bound. And so sort of binary search could take a very long time if I, right? So I want to be a little bit careful. So I'm going to look for a slightly better lower bound than 0.
do a linear search through all your things, see if one of them fits in your bag.
Exactly. I mean, I can obviously try putting individual items into the bin, into the knapsack, right? So the minimum possible thing is the max of the PIs. I mean, obviously, if there are things that don't fit in the knapsack at all, I can ignore them. They're irrelevant. So whatever the largest profit is, I can get that. Okay. How about an upper bound? Can we give an upper bound on the profits that can fit in the knapsack? Yeah?
Some of all the profits.
Some of the PIs. OK. Now, what's nice about these, to go between the max of the PIs and the sum of the PIs, is that these have a ratio of n between them, right? My maximum bound is at most n times my minimum bound. Okay. So now it's actually convenient. We could talk about binary searching on these numbers, but I'm going to phrase it slightly differently. Let's just try all powers of 1 plus epsilon in this range, all integer powers. Okay, so you know, if this is 1, then I'll look at 1 plus epsilon, 1 plus epsilon squared, 1 plus epsilon cubed, so on and so forth. Okay. Now, the nice thing about these powers of 1 plus epsilon is that if I succeed with one of them, and the next one is too big, then I know that I'm within a 1 plus epsilon factor of the optimum solution. Right? So find the largest that works. And this is within 1 plus epsilon of the true optimum, because any larger power of epsilon doesn't work, and so the true solution is between my power of 1 plus epsilon and the next power of 1 plus epsilon. Okay. Now, how many powers of 1 plus epsilon are there in this range? Well, there are log base 1 plus epsilon of sum of pi over max pi, which is at most log base 1 plus epsilon of n, which is equal to log n, or approximately log n over epsilon possible powers. So I have to try this many different powers of 1 plus epsilon using the scheme that we just outlined over here to see which one works and which one doesn't. Now, in fact, sorry, yes, go ahead. Yes, so this is, if you want to be really efficient, right? So this is already fine, right? You're only doing log n different powers. But if you want to be really efficient, you recognize that actually you can just do binary search among the integer powers, right? So that is going to reduce the number of trials I need to log of log n over epsilon, which is logarithmic in n, but also logarithmic in epsilon, which is great. Unfortunately, the individual trials still cost me n squared over epsilon. So that determines the epsilon dependence of this algorithm, is that it is basically linear in epsilon. Okay. Questions? Yeah?
What happens if you use like an output of the algorithm on a p that's too large and the next guess of the p?
Oh, so you could actually be more adaptive about what do you learn from the first p in order to. So that adaptivity will probably let you squeeze even more out of this part of the runtime, this log n over epsilon or log of that. Unfortunately, you're still using this as your oracle. So you're at least going to be spending n squared over epsilon time. And so, yeah, you can get arbitrarily close to n squared over epsilon, but you're never going to be able to beat that n squared over epsilon. Okay. All right, so this gives us now our fully polynomial approximation scheme, right? So you notice that we have a running time that is polynomially dependent on n, the size of the problem, and also epsilon, the accuracy to which we want to find the solution. So if you want a solution that's within 0.01 of optimal, you have a polynomial time algorithm for finding that solution. Okay. Now, as you might expect, this technique of sort of scaling things, rounding to integers, using a dynamic program to get the solution for small integers, that's a pretty general technique, right? You can imagine applying that to all sorts of numeric approximation problems, okay? It turns out that in a strong sense, it's the only technique, okay? So what I've shown you here is a way to sort of reduce from an algorithm that works for small integers into an approximation algorithm. Turns out you can also go the other way. Okay, so what characterizes the algorithm that we started with, right? Our exact algorithm had runtime n times p, where p was sort of the numeric size of the solution. We've seen that before when we were looking at max flow algorithms. The first max flow algorithms that we looked at had this characteristic as well. And I think I gave you the definition then of these pseudo-polynomial algorithms. Right? The running time is polynomial in the input size, but also it's polynomial in the value of the solution. Right? We then made a very important bit of progress by getting running times that were polynomial in the log of the solution, in the number of bits in the solution, because that could be considered part of the input size. Right? So the pseudo-polynomial algorithms, they're much weaker. Right? Their running time depends on the value of the solution, since you only need, right? You can use n bits to specify a number that is of magnitude 2 to the n. So it's still a size n problem, but the running time of this algorithm is 2 to the n. So it's not really satisfactorily polynomial, but so we give it this sort of pseudo-polynomial characterization. Okay? Sorry. So we had a pseudo-polynomial algorithm, and we showed how to transform that into a fully polynomial approximation scheme for Knapsack. Right? Well, now I'm going to show you how to go the other way. Right? Suppose that we have a fully polynomial approximation scheme for Knapsack. This isn't very hard to suppose because I just gave you one. Right? But suppose that I have any pseudo-polynomial, so suppose I have any fully polynomial approximation scheme for Knapsack. I'm going to give a generic transform that turns that into a pseudo-polynomial algorithm. Yeah?
Is this true only for Knapsack?
No, so this is the point. I'm giving the example for Knapsack, but you can prove this quite generically. The only hard part about proving it generically is defining what you mean by a generic problem with a fully polynomial approximation scheme. Right? So you just need to talk about what is an instance, what is a solution, what is a value of a solution. But if you phrase things in those abstract terms, you can show that any algorithm that has a pseudo-polynomial solution, algorithm has a fully polynomial approximation. Any problem with a pseudo-polynomial algorithm has a fully polynomial approximation scheme, and any problem with a fully polynomial approximation scheme has a pseudo-polynomial algorithm. Okay? But let's just show it for Knapsack so that we don't have to get into the mess of defining a more general class of problems. How do I take a fully polynomial approximation? So remember, this is a scheme where you can give it any epsilon that you want, and it will find a solution that is within epsilon of the optimum for any input instance. Okay, now I want to turn that into a pseudo-polynomial algorithm. So a pseudo-polynomial algorithm is supposed to be fast if the solution to the problem is of limited size. Right? So suppose that the input instance has optimum p, as we've been discussing. How can I use my fully polynomial approximation scheme to find an exact solution to this problem? Well, the only thing I get to control in my fully polynomial approximation scheme is epsilon. Right? So I have this black box. I get to give it a problem, and I get to tell it epsilon. So what epsilon would be a useful one to tell this black box? Yeah?
1 over p.
Right. So let's just set epsilon equal 1 over, let's use p plus 1 just so I don't get in trouble. Shades of our scaling of approximation, of absolute approximation algorithms, right? So that means that we will find a solution of value p times 1 minus 1 over p plus 1, right? Which is greater than p minus 1 and is therefore equal to p if we're talking about a problem with sort of integer inputs or integer solutions. So that's all it takes, right? So we had to work harder to get from the pseudo-polynomial algorithm to the fully polynomial approximation scheme, but we did it by scaling. And going back the other way basically involves a similar kind of scaling. We're just scaling epsilon to fit the value of the solution. Yes?
Doesn't the approximation work, though, for non-integer prices as well?
Yes, it does. But that's kind of the point, right? In the definition of pseudo-polynomial comes this assumption that your input values are integers and that your output solution has an integer value. Fully polynomial approximation scheme does not, you don't only talk about it having integer inputs. A fully polynomial approximation scheme is supposed to work for arbitrary inputs. Okay? But the point is that if you have a pseudo-polynomial algorithm, then you can get a fully polynomial approximation scheme by rounding anything down to integers and feeding it into the pseudo-polynomial algorithm. Okay, so that's our first example of an approximation ratio better than 2. Right? It's a lot better than 2. We can get as close as we like. And it lets you deal with a quite large class of problems. However, those problems are, in a sense, easy. Right? The fact that we were able to give this kind of algorithm is sort of undercutting the hardness of the problem. Right? Because after all, we can solve exactly this huge class of instances of the problem. Right? We're only getting into trouble when the numbers get really large. And so from the complexity side of computer science, there's this notion of weakly versus strongly NP-hard problems. So we know what NP-hard means, but we can sort of refine this definition by talking about the numbers that are involved in the input to the problem. So strongly NP-hard what that means is a problem with strongly NP-hard is that it's NP-hard even for small numbers. In the input. Okay? So what we've given here in Knapsack is not a strongly NP-hard problem. It's easy to solve if the numbers are small. And so Knapsack, although it's NP-hard, is only weakly NP-hard. Okay? There are other problems, most obviously the ones that don't have any numbers in them, that are strongly NP-hard. They remain NP-hard even if the numbers that are provided as part of the input are small. Okay? So what's the relationship here? Well, a strongly NP-hard problem cannot have a pseudo-polynomial algorithm. Right? If it's NP-hard for small numbers, then there can't be an exact algorithm when the numbers are small. In other words, there can't be a pseudo-polynomial algorithm. So what we've got here is sort of the tip of the iceberg of this class of problems that are NP-hard, but they're only weakly NP-hard. They're not strongly NP-hard. And as a result, they do have solutions, polynomial time solutions, when the numbers are small. And we can use those small number polynomial time solutions to get fully polynomial approximation schemes for them. So these three notions of pseudo-polynomiality, weak NP-hardness, and fully polynomial approximation schemes are very tightly tied together. Okay? Questions? Yes?
How small is small now? Can we consider not strongly?
So the formal definition of strongly NP hard is that it has to be NP hard, as which is sort of has to do with sizes of the input and such, even when the numbers are written in unary. Okay. In other words, a number of value t takes t bits to write down. Okay. If it's NP hard under that definition, then it's strongly NP hard. Other questions? Okay, so now that we've taken care of this class, and so we've given an approximation scheme for it and immediately said, well, these aren't interesting problems, they're too easy. Let's take a break, and then we'll look at a slightly harder class of problems for which you can still say interesting things about approximation. Okay, so take 2 minutes. For our next trick, we are going to look at a more sophisticated kind of enumeration. Where instead of enumerating over numeric values, we're going to enumerate over subproblems and over the structure of subproblems. And that's going to let us construct some new and more powerful approximation schemes. So we're going to be looking at a technique called k-enumeration. And I'll demonstrate it by example on this problem we looked at last time of Cmax. So I don't remember if I wrote up this notation, but again, in scheduling theory, there are literally thousands of different problems. And it got so complicated that they had to invent a notation for describing the problem. Okay? And so the notation is that first you have one position to describe what are the characteristics of the machines. So here we're looking at a set of parallel identical machines. You might instead want to look at a single machine problem. There are a bunch of interesting scheduling problems on single machines. You might want to look at problems where the machines some are faster and some are slower. And you can take that into account when you decide where to put your jobs. Or you may want to look at completely unrelated machines. Like, this is a lathe and this is a drill press. And so some jobs can run on the lathe and not on the drill press, and some jobs can run on the drill press and not on the lathe. And you have to take that into account as you're doing your scheduling. And then you have various objective functions. So here is Cmax. This is the problem of minimizing the maximum completion time of any job, right, which I looked at last time. You might also be interested in the sum of completion times, which is also the average completion time, right? You might be interested in the sum of the latenesses of the jobs. If every job has a deadline, you might want to wonder how far you go over the deadlines for the various jobs. Or you might be interested in some weighted sum of the indicator variables that tell you whether a job was late or not. So it's not like a linear function of lateness, but just you immediately get penalized by Wj if job j is late. Now, of course, in order to talk about these late jobs, you may need to have some deadlines for the jobs, which you put into the middle bars. By writing dj. You might have some release dates for the jobs before which they can't be executed. You might have a preemption feature in your scheduling problem where you're allowed to stop a job midway and come back to it. You might have precedence constraints on your jobs that say you can't do this job before you did this other job. Right? So you can see the combinatorial explosion happening, right? You've got all these different possible classes of machines. You've got all of these different funny kinds of characteristics of the jobs and constraints. And you've got all of these different objective functions. You multiply those all together, and you've got so many problems that you actually need to have a website that is dedicated to classifying scheduling problems according to whether they are polynomial time solvable or NP hard. And sort of you can go, if you Google the scheduling problem classifier, you can go type in a scheduling problem, and it will tell you what is the minimal NP hard problem that is still harder than the one that you typed in, and the maximal polynomial time solvable problem that is still easier than the one that you typed in. And it's a great place, like if you just want a theory problem to work on, there's a few thousand on that website, right, to sort of take some new combination of scheduling constraints and decide whether it's polynomial time solvable or not. And the thing is that there's lots of money in this, because this is what like the airlines care about, and the train companies, and every manufacturer with an assembly line. They're all solving scheduling problems. And I remember I was visiting IBM research looking at postdocs, and the guy there told me how they saved some steel milling company $70 million a year by shaving 1% off the value of an objective function in a problem like this. Okay. Yes?
So if
What is the notation that we're using P double bar Cmax?
Oh, it's not a bar. It's just that it's empty right now. This is a space where I would put any of these. So I might say something like P prec some Cj to talk about, OK? But again, for now, we're just talking about this problem, this one that we started on last time. And we're going to try and come up with a better than 2 minus 1 over m solution. OK? So does anybody remember what was sort of what was the problematic case for Graham's rule and the sort of insight that we had about what kind of inputs would really foul it up? Yeah?
Also small ones and then very big ones again.
Yeah, so the problem was when you got this really big job at the end, right? And so if you think about the way we analyzed that problem, right? We said, well, there's two lower bounds. There's the average load, and then there's the biggest job, right? So if the biggest job is very small, then we're actually in very good shape, right? Because our bound is equal to the average load plus the biggest job. So if the biggest job is small, then our approximation is very good, right? So what kills Graham's rule is large jobs, okay? And that suggests that we should do something different with the large jobs. So one thing that we could do is just schedule them first and hope that the small jobs kind of pile in and smooth everything out. So that's known as longest processing time first. And you can prove that that actually gives you a 4/3 approximation to the optimum. But we're actually going to do better. We're just going to take care of the big jobs by a completely different process. Okay? So if I tell you, here are 3 big jobs. Everything else is small, but I've got these 3 big jobs to worry about. What would be the natural thing to do? Well, brute force, right? Just try everything possible with the big jobs and see which thing works out well. So this is the idea of k enumeration, is that we're going to take the big part of the k biggest jobs, and we're going to schedule them by brute force, by enumerating all possible schedules. And then we're going to pile in all of the small jobs and argue that that doesn't hurt very much because Graham's rule is very good with small jobs. Okay. So let's schedule the k largest jobs optimally, and then schedule the remainder greedily. Okay. So what do I mean schedule the k largest jobs optimally? We don't know what the optimum is. How can I schedule the k largest jobs optimally? Well, that's shorthand for try everything. Okay, I'm just going to try every possible scheduling of the k largest jobs. And then for each of them, I'm going to proceed to schedule the remaining jobs greedily. And I'll take whatever comes out as the best solution. So somewhere along the way, since I'm trying every possible combination of the k jobs, I will pick the optimal one. And so my analysis is going to focus on what happens in that thread of the computation where I've picked the optimal schedule. Okay. On the other hand, this trying of everything is certainly going to impact my running time, and I have to take account of that when I do my analysis. So actually, let's talk about that first. What can we say about the running time of this procedure, where I try every possible schedule of the k jobs, of the k biggest jobs, before greedily scheduling everything else? How long is that going to take me?
How many machines do we have?
We have m machines. So how many ways are there for me to try scheduling k jobs on m machines? Yes, good. So there are m to the k possible ways to schedule these k jobs optimally. And then after that, it's linear time to schedule the n jobs. Actually, it's probably n log n, so I'll put one of my tildes over here. Okay. So that means that we have an order n times m to the k running time for our algorithm. Now, is that a good running time or a bad running time? Well, it kind of depends on what I'm taking for m and k, right? Let's keep that in mind as we look at the analysis. So what can we say about how good our solution is? I'm just going to refine the Graham's rule analysis. So if you look back at what we proved last time, I claim that in fact what we proved is that my algorithm, my greedy algorithm that is putting all of the other jobs onto the few that I scheduled optimally, takes at most the optimum value plus the k plus first job processing time. Okay. So this is the k plus 1 largest job. Okay. Why is that? Who can explain how I just sort of tweak the analysis of Graham's rule to state this? Yeah?
Well, because Graham's rule sets the largest job because you're scheduling all the jobs, and now you know the largest job that you're scheduled greedily is the k plus first largest job.
Good. So again, running through Graham's rule, right? Let's just let I be the last job to finish. Sorry, J. Last job to finish. Right? Why is it the last job to finish? Well, it got scheduled on some machine. But when it was scheduled on that machine was the least loaded machine. Right? So at the time that it was scheduled, the machine load was less than opt, because it was the minimum load. And the minimum load is less than the average load, which is less than opt. Right? Which means that its completion time was less than opt plus pj, which of course is less than opt plus pk plus 1, unless there's one thing we have to worry about that we didn't have to worry about with Graham's rule. Right? So what I'm analyzing here is the case where the job that finished was scheduled greedily. Right? In Graham's rule, all of the jobs are scheduled greedily. But here, we schedule some of the jobs non-greedily. So what if one of those is the last job to finish? What if the last job to finish is one of the k biggest jobs? Yeah?
So if that was the last one to finish, that means your objective didn't get any worse when you added all the little jobs, and you had an optimal solution at the beginning, so you're actually optimal.
Exactly, right? So if the last job to finish wasn't one of the greedy jobs, then the greedy scheduling didn't change the objective at all. And I scheduled the k jobs optimally. So in fact, if the last job is one of the k biggest, then my schedule is optimal. Now, one thing to be careful about, right? I'm not saying you schedule, I'm not considering scheduling these k jobs optimally in isolation. Right? I'm not looking at the best schedule for these k jobs. I'm looking for how these k jobs are scheduled in the optimum schedule that includes all n jobs. Okay? So knowing that there's a bunch of other jobs coming may actually change how you want to schedule these k jobs. But I schedule according to that. I schedule these k jobs knowing that there are other jobs coming. And so if one of those is one of the last to finish, then my schedule is actually an optimal schedule for the n jobs that I have. So either I'm optimal or I'm within opt plus pk plus 1. Okay. So that tells me that if pk plus 1 is small, I have a great approximation, right? So how big can pk plus 1 be? Well, in isolation, right, if I just look at it, it could be arbitrarily large. But what does it tell me if pk plus 1 is large? Yeah? The k other jobs are at least that big. So however big pk plus 1 is, I have at least k jobs that are bigger, or that are as big. And what do I know if I have if I have a bunch of really big jobs? Well, that can be used to lower bound the optimum. Okay? So notice that the optimum is at least, it is lower bounded by this average load, right? Sum of pj over m. Right? That's one of the bounds that we used in Graham's rule. Right? But if pk plus 1 is large, then the k largest jobs are small. So in particular, this is at least k times pk plus 1 divided by m. Right? So now that I have, and so if I have this bound, right, that opt is greater than or equal to k over m pk plus 1, that of course implies that pk plus 1 is at most m over k times opt. Right? But if I've now upper bounded pk plus 1, I've said pk plus 1 can't be too big, then I can conclude that my approximation can't be too bad. Right? So now I can conclude that my algorithm achieves a value of opt of I plus k over m times opt of I, namely 1 plus k over m times opt of I. Oh, sorry, m over k. So now I have an approximation bound for my algorithm. Okay. And what's nice about this approximation bound is that, if I want to achieve a certain ratio, a certain approximation, I just need to pick k appropriately. So if somebody tells me that they want a 3/2 approximation, I just need to set k equal to m. Right? So in particular, this is my epsilon for my approximation algorithm. Right? So epsilon is equal to m over k. In other words, I need to set k equal to m over epsilon if I want an epsilon approximation. But now we can go back and look at our running time, order nm to the k. Right? And we discover that we have a runtime of order n times m to the m over epsilon. Is that good or bad? Well, that depends on m. Right? But in particular, this is polynomial in n for fixed m. So if I need to schedule on 3 machines or 4 machines or 5 machines, any constant number of machines, I now have a polynomial approximation scheme. For any desired epsilon, I can choose k corresponding and get an algorithm whose running time is actually linear in n for any epsilon. But from another perspective, even ignoring the assumption of small m, the dependence here on epsilon is worse than it was in our knapsack example. Right? Here, the running time really blows up with epsilon, even though it's polynomial for any fixed epsilon. So this fits the definition of a polynomial approximation scheme, but not of a fully polynomial approximation scheme. Okay? And so polynomial approximation schemes are still nice to have. You can get as close as you like to 1, but the particular polynomial you're going to be using in order to do that tends to be kind of painful. Okay. All right. But that requirement of fixed m is kind of unfortunate. So let's get even more sophisticated and figure out how to get a solution that is polynomial for any value of m. Okay. So for large m, we're going to sort of combine all of the ideas that we have looked at today. We're going to combine the sort of enumeration idea, the sort of trial possibilities idea, with the sort of rounding and and dynamic programming approaches that served us well in Knapsack. Okay. So again, we're following sort of the Knapsack perspective. I'm going to want to start by talking about a problem where the inputs are small. But here I'm not going to talk about small numbers. I'm going to reduce the complexity of the problem in a different way. So let's suppose that there are only k distinct job sizes. Okay, so this is analogous to assuming that we have small integers in Knapsack. It's going to let us do a dynamic program that doesn't get too big. Okay. In particular, since there are only k distinct job sizes, describing the solution becomes easy. Okay. To describe one machine and the jobs that are running on one machine by just counting the number of jobs of each size that are on that machine. So it becomes easier to specify a solution. Instead of specifying exactly which job goes on which machine, I just need to count the number of jobs of each size on a machine. So I can define a machine type, which is equal to some number of the first size jobs, some number of the second size jobs, up to some number of the kth size jobs. Now, how many machine types are there? How many different ways can I fill in these numbers that specify the machine? Right? So there are n jobs, and I'm not going to be picky about how many of them have each size. I can put a number between 1 and n in each of these places. So there are n to the k types of machines. And that's kind of nice because that looks like a polynomial. Right? So we haven't yet made anything exponential. Similarly, there are actually only n to the k possible input instances. Right? Because an input instance is also just a specification of how many jobs of each type there are. It doesn't matter which jobs are which. We just need to know how many there are. Okay. So let me ask the following question. Can we decide which instances specified in this way are feasible for m machines? Well, the answer is yes. And it's, again, dynamic programming. Yes, Arne?
What do you mean by feasible?
That is, I've got these machines. Oh, sorry. So I left out something important. So we're looking at these number of types. Some finish within a given target time t. Okay. So this is going to play the role of p in the Knapsack problem. It's sort of, what do we think we should be able to achieve? And we're going to sort of binary search around to find the achievable t. So some combinations of jobs have total processing time less than t. And so if we put them all on one machine, then we can finish all of those jobs within time t. Okay? And those are the types that those are the machine types that I'm going to pay attention to, is sort of combinations of jobs that can be completed in time t. Okay? So if I take m machines and give each of them a set of jobs that can be completed in time t, then I've created a schedule of some jobs that can be completed all in time t. Okay? Now the question is, for which input instances, which is a certain number of each kind of jobs, is it possible to define that sort of schedule of things that can be completed in time t? Okay. And we're going to answer that question using a dynamic program again. Namely, if I'm given sort of the feasible instances on m-1 machines, how do I decide what are the feasible instances on m machines? Right? This is a collection of jobs that can be completed in time t using m-1 machines. How do I enumerate all the possible collections of jobs that can be completed in time t using m machines? Yeah?
You look at all the jobs that, like all the machines that complete a certain number of jobs in t time, and then you add all those jobs.
Exactly. So what we do is we just consider adding one machine of each feasible type. Right? If I have a set of jobs that can be completed with m-1 machines, and now I try tacking on one more machine with some more jobs, that gives me a set of jobs that can be completed with m machines. Right? And so this gives me my dynamic program. I start with the set of jobs that can be completed with 0 machines. Right? And then I build up to the sets of jobs that can be completed with 1 machine, and then 2 machines, and 3 machines, and 4 machines, and so forth. So I just keep working my way up until I have all the sets of jobs that can be completed with m machines. And the reason that this can be done in polynomial time is that there aren't that many sets of jobs, and there aren't that many different kinds of machines to consider. So this takes n to the order k time to find all feasible instances. Right? So this is the sort of the analog of the pseudo-polynomial algorithm. This is saying if we have an input instance which can be solved, if we have an input instance which is small in the sense that there are only a few different types of machines, then we can solve it in polynomial time. Where here now we're polynomial in the number of different types of, in the number of different sizes of jobs. What are we going to have to do in order to turn that into a general algorithm? Well, we're going to have to round somehow. We're going to have to turn a set of jobs of many different sizes into a set of jobs of just a few sizes, and then apply this technique. So that's where we'll pick up on Friday.